What we're going to work on today are going ahead and, if we've got a bunch of operations combined, how to handle the sig digs carefully in those type of situations. Do two things. First of all, we're going to do a quick review of the order of operations when evaluating expressions, and we did that very briefly, I think, the day before yesterday. And then we're just going to do some practice. We're going to evaluate expressions involving several operations and pay special attention to keeping the correct number of significant digits. We're going to do a few problems that involve exact values. Those problems, all we're paying attention to is the order of operations. We don't need to be concerned with sig digs if we know that all the values are exact. And then we'll do a few that are considered measure values where we need to pay attention to the number of significant digits. Well, first of all, your order of operations. As you know and as you've said before, we're going to cover it to make sure that we're complete and not missing anything, but certainly shouldn't be anything new here. You always want to handle all your operations within parentheses first. Within any set of parentheses, you're still going to follow the proper rules of order or order of operations, and that means you always handle what to begin with? Once you're working inside parentheses, you always do what first? You're always going to take care of your exponents and roots. Powers and roots have to be evaluated next. Well, next might not really be the right word there, but first, even if you're working inside of parentheses. Powers and roots because they're really just different ways of writing the same thing. Now we're going to do all the multiplication and division. Division is really just multiplication by a reciprocal. And so multiplication and division are in some sense the same operation. Sometimes people are incorrectly instructed to do multiplication before division. That's not always true. Multiplication and division get done at the same time, working from left to right. And finally, we wrap up by doing all the addition and subtraction again, working from left to right, because subtraction is really just the addition of a negative number. So they are really, in some sense, the same operation. With that in mind, all we're going to do is work through some examples. So, here we go. We're going to consider these to be exact values. We're not concerned with significant digits in this problem. All that we're concerned about is the correct order of operation. Okay. Well, let's take a look at this. First of all, follow the order of operations. Where do we need to start? We need to start with the parentheses. So working inside the parentheses, we will handle all the exponents, and we're going to work from left to right. So we start out with 3 squared, which is, of course, 9, plus 64 to the 1/3. That's a great problem for your calculator. What is 64 to the 1/3? 4. Over. Now, since we're still working inside parentheses, we really should finish this off. 9 plus 4 gives us what in the numerator? Well, 13. Nothing fancy there. Now we can move on to the denominator. In a sense, a fraction bar itself acts as a grouping symbol. When we've got a whole fraction like this, we figure out what the whole numerator value is, and then we figure out what the whole denominator value is. So in the denominator, 8 plus 8 divided by 4, we need to first of all divide. We need to take that and write it as 8 plus 8 divided by 4 is 2, so this becomes 13 over 10. That is the exact value. We're done. 13/10 is the value of that expression. 13/10? Either way would be fine. We could write that as 1 and 3/10. Yeah, this is improper. 1 and 3/10 is probably a better answer. Either one of them would be okay. Good question. 1.3 would be okay. That's still exact. You wouldn't want to convert it to a decimal if it didn't work out to be an exact decimal, because then you wouldn't be able to write it without rounding. Make sense? Good. Look okay? Another one. Again, one more with exact values. We're going to look at the sig digs in a minute, but one more with exact values to focus on the order of operations. Okay, radicals act as grouping symbols. Anytime you've got a radical, it acts like a set of parentheses, and we need to figure out what the value of the radicand is first. So what should we do? Start with the one on the left. The square root of 6 times 54 is actually just the square root of 324. We are going to assume y, just because I told you, and your book usually does. We're going to assume principal root here because actually there's two solutions to this, right? What is the square root of 324 technically? Plus or minus 18. We are going to assume the principal root here. And so we're going to say that that value is 18. Okay, minus the fifth root of, what is our value in parentheses? 10 to the third plus 24? 1,024 is correct. So the fifth root of the 1,024, it's a fine time to use your root button on your calculator. Just as a side note, how could you write this? I'm going to immediately erase it, but how could you write this as an exponent? You could write this as 1,024 to the what power? 1/5 power, right. So either way on your calculator, you're going to get the same value. And what is that value? 4. Plus, this one you shouldn't need your calculator for. The cube root of 5 cubed. What happens to a number if you cube it and then take the cube root? Yeah, you're right back where you started. And you'll end up with 5. Now, if you don't spot that and do the work on your calculator, as long as you do it right, you're going to get the same thing. But we end up with 18 minus 4 plus 5, and so the value of this expression turns out to be 19. 19. 19? Good. All right. Look okay? Okay, now we're going to mix some significant digits into the batch. So we have to do the same thing, but now we need to be careful to keep the correct number of significant digits after each step. Before too long, we're going to introduce a shortcut rule for handling significant digits, but we want to make sure we can do it completely and thoroughly first before we start cutting corners. We want to compute this value, and we want to keep the correct number of significant digits in our answer. Yeah, we want to do that division first, and it's going to turn out to be some long decimal. How many sig digs are you allowed to keep on this first step of division? 4. 4 in our dividend, 5.12 in the divisor. Nope, it's always the fewest. So we have 4 here, 5 there, so we can keep 4. If that would have been just 5.12 with no zeros, then we'd only be allowed to keep 3. So we're going to keep 4. 17.85 divided by 5.12, we can keep 5.1200, and we can keep 4. So that turns out to be 3.486. There's our 4 sig digs. We kept the same number by doing that step. And now we're going to try and add that to 8.2401. All right, now we can go ahead and perform that addition. Again, the emphasis here on this first step was when multiplying or dividing, you don't care where the decimals are, you just count how many significant digits and keep the same number as appear in the, let me start that over. You look at both numbers, and whichever one has the fewest number of sig digs, that's how many we can keep our result. All right, so now let's do this addition. These are going to be added together to give us the cube root of. Now, what's the rule for addition? Exactly. It's the placement. So Here we're precise to the nearest thousandth. Here we're precise to the nearest 10,000th. Our sum can only be precise to the nearest thousandth. 3 decimals, 4 decimals, we can only keep 3 decimals. And if we do that, we get 11.726. 11.726. Now we're going to take the cube root of that, and the cube root, any root for that matter, the rule for taking a root is you keep how many? Any radical or root, how many sigdigs do you keep? However many are in your radicand. So we have 5 here, we'll take the cube root. And it turns out to be a long decimal, but when we keep 5 significant digits, you should find that it works out to 2.27186, and so we have to call it 9. There's our 5 sigdigs. .2719 is the correct value with the correct number of significant digits. Same instructions, different problem. We want to keep the correct number of significant digits in this result. I'll write it up here. Well, what should we attack first in there? Top left, 6.25 to the 1.4th power. Now, how many sigdigs will we have when we compute that? 3. There's 3 in the base. The number and the exponent don't matter, and so we're going to keep 3, and that turns out to be 13.0. Yep. Now to that we're going to add 9.00. Let's figure out what the bottom value turns out to be here just to save a little bit of writing. 72.33 to the 0.5 power. We can keep 4 significant digits when we evaluate that. Let me know if you match this. I have 8.505 when rounded. Okay, good. 8.5047 is what it is before rounding. Okay, well now we can clean this up just a bit, and we end up with, now let's do this addition in the numerator of that fractional value. 13.0 plus 9.00. What do you get when you add those two together with the correct number of significant digits? 22.0. Good, Kyle. 22.0. 10th, 100th. So the best we can do when adding, 10th. 22.0 over 8.505. This is all to the 2.5 exponent. Now, of course, we need to divide those. We're going to divide those, and we can keep 3 sigdigs. 3 sigdigs divided by 4 sigdigs will leave 3 sigdigs. 22 divided by 8.505 gives us 2.5867, so we have to round it to 2.59. 2.59 will be our 3 sigdigs. That's going to have an exponent of 2.5 on it. Everybody agree with that? Okay. And then finally, we can evaluate that exponent. 2.59, we're going to raise that to the 2.5 power. We're going to keep 3 sig digs because that's how many are in the base, and we end up with a result of 10.79566. We're going to call it 10.8. That's the value of that expression with the correct number of significant digits. We are going to do one more. This is the last one. This is a formula for computing interest. You put money in an investment or take out a loan for that matter. It'll grow and it'll compound itself every time the interest is compounded. This is a formula, and we're going to plug values into the formula. We're going to do a lot more of this in a few days, but it's a sort of a look ahead using the ideas that we've learned so far. Our formula is P times 1 plus R over N with an exponent of N times T. And we have the following values. We know that P is equal to $400 with the precision of the nearest penny or hundredth of a dollar. The R that we have here is an exact value of 0.065. N in this formula represents the number of times per year the interest is compounded. That would be quarterly, and that turns out to be 4. And again, we're considering that to be exact. And we're going to have this invested over a period of 12 and a half years. Note here that the 1 in the formula is considered to be an exact value. Okay, so that 1 in the formula is considered to be an exact value. So what are the only 2 numbers that we actually have to pay attention to as far as significant digits are concerned? The principal, $400, is not necessarily exact. To the nearest penny it is, but and then our time period of 12.5. The R and the N are said to be exact values, so we don't care how many sig digs there are there. It's not going to factor in, nor does that 1. So with that in mind, let's go ahead and rewrite this, filling in the values that we know. This turns out to be 400.00 times 1 plus 0.065 over N, which is 4, to the NT, which will be 4 times 12.5. I'll put those in parentheses to clarify a little bit. Okay. So we need to do that division inside of the parentheses first. 0.065 divided by 4. Those are both exact values, so we're going to keep all the significant digits that our calculator reports. 0.01625. Now, what will our exponent on that be with the correct number of significant digits? For the exponent, we're going to have 4. How many sig digs are on that 4? There's actually only 1 there, except we know that it is an exact value. And so we consider it to have hundreds of significant digits. It doesn't matter. So the 12.5 is not exact, though, and how many sig digs are there? 3. So how many will we actually keep? Yeah, so our exponent becomes 4 times 12.5 is 50.0. There's 3 sig digs on our exponent. So let's stop there for a minute. We did 2 steps combined here. The 0.065 was exact and the 4 was exact. That's why we have so many sig digs here, and this is considered to be exact. Since they're exact, we pay no attention to how many sig digs. We keep as much precision as we want. Exact times 3 sig digs give 3 sig digs. Okay up to there? All right, let's finish this up. So we have 400.00 times 1 plus 0.01625 is 1.01625 with an exponent of 50.0. Okay, well, this is a common place for arithmetic error to be made. I won't claim to know why, but a very common misstep here is to, I should say that a very common step that's done incorrectly is to multiply these two values together. But by our order of operation, what do we have to do? We have to do that exponent first. Now we've got a bunch of significant digits here. 1, 2, 3, 4, 5, 6 to the 50th power. So how many sig digs are we going to have in this value? 6. Doesn't matter how many there are in the exponent. So this is going to become 400 times whatever that works out to, and it's going to be fairly long, but we're going to keep 6 sig digs. 1.01625 to the 50th power, 2.2388. There's 5 sig digs, so we can keep one more. 6, 5 are the next two digits, so we want to call it 7. I want to make sure, did everybody get this value on your calculator and see why those are the 6 digits we're keeping? Okay. Well, finally, we can do the multiplication here. And how many significant digits are we going to be allowed to keep in our answer? Because our last step is multiplication. We have 5 and 6, so we can keep 5. So we're going to take that value, 2.23887 times 400.00, or just 400, because your calculator doesn't care about significant digits. $895.548, we have to call it 55 because that's our last significant digit. Now I did drop a dollar sign here. The 400 had the units of dollars, and so our answer will have an answer of dollars. Now what this formula, we're going to be using this formula a little bit later on, but just as a little side note, what this formula says is that if you take $400, which is your principal, invest it at a rate of 6.5%, compounded 4 times per year for 12.5 years. At the end of that 12.5 years, your investment of $400 will be worth $895.55. Now, if you really want to save a lot of money, you want to make this part of the equation grow as fast as possible. And what's the quickest way to make this part grow as fast as possible? What number can you change here that'll make this get large very quickly? Your interest is one factor, but the other one, unfortunately, is time. It'll grow as big as you want if you wait long enough. All right? Unfortunately, it doesn't pay to invest money for say 200 or 300 years because, well, your great-grandchildren will enjoy it. Does that one look all right? Okay, that's where we're going to stop. You should be able to now take all the stuff that we've done, the order operations, and be able to do several computations and always keep the correct number of significant digits. So we'll stop there.